In this video, I wanted to talk about synthetic division. Synthetic division is a super great shortcut for doing long division, which in my last couple lecture videos, you heard me talk way too much about that. But my point is there is a shortcut. There's a very, very fast way to divide polynomials, specifically when they are degree 1. Now, first, in these first couple videos, I wanted to talk about, well, what is synthetic division? Why does it make sense? And then kind of show you how you can do it really quickly. But to begin with, I wanted to sort of compare how do we do long division and how does synthetic division work, and why does it make sense to do synthetic division? Because a lot of times students will learn how to do synthetic division, but they won't really get it. And the problem with that is that how are we ever going to remember it in the long run? So probably a lot of you have seen synthetic division. Like I said for myself in a previous video, I never really learned how to do this before when I was a student. So it's a skill I had to kind of learn on the fly. But it's very, very helpful technique for division of polynomials. Anyways, so I'm going to turn on speed mode and let's just do the long division here and solve our answer. So this would be 2x cubed minus 4x squared, change the sign. This would give me x squared, drop, matching x squared with x would be plus x, multiplying through would be x squared minus 2x, changing the sign would give me negative x, dropping the plus 2 would be negative 1 match, negative 1 into x minus 2 would be negative x plus 2, change the signs, add, eliminate, eliminate, 0. And so what I can see from doing this division is that 2x cubed minus 3x squared, blah, 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 is divisible by x minus 2, and our answer is simply 2x squared plus x minus 1 with no remainder. Cool. And for me, I've taught division a lot of times. I'm pretty fast at it, I can, but for most people, it takes quite a bit longer, and I wouldn't expect them to be able to do this quickly. That's the whole point of synthetic division, is to simplify this process to really what's the bare bones mathematical steps I need to do to figure out the outcome. And basically, the step-by-step instructions are below. You want to first start off by, and I probably need to update the step-by-step because now that I'm looking at it, I didn't do such a good job of writing this a couple years ago. But to begin with, you always want to start off by setting it up. Basically, you're going to take your original polynomial, still going to put it on the inside. And notice, you don't write the entire polynomial, you only write the coefficients in order. And on the outside, you might think this is a typo, but it's not. You always want to put the opposite sign to the divisor. So, and just, I think I said this earlier, but just in case I didn't, this synthetic division only works when dividing by simple binomials, like linear functions x minus 3, x plus, it doesn't have to be minus, it could be plus, but basically a degree 1 polynomial like this. If I was trying to do this, you cannot use synthetic division to do things like this. It just does not work. I wish it did, but there is no simpler process for it. Well, saying there's not any is probably not true, but synthetic division only works for ones like x plus 4, x minus 3, or so on. It does work with fractions too, by the way. We might look at an example of, say, x minus 1/2 or something like that as we progress through this chapter. Anyways, you always need to put the opposite sign over here. Instead of putting minus 2, you put plus 2 and you drop the x. Notice you only need a single number, and I'll try to explain why as we're looking at this. But basically, that would be the setup. Once I have it set up, then I'm going to follow these steps. It says drop the first inner number below the line. So I'm going to drop this down there, 2. Also notice that the division bar is upside down. Not really necessarily a good reason for that. Some books actually keep it the other way, but most people will invert the division bar. It doesn't really matter. And the second line is indicating, well, we'll see as we go. So we're going to drop the first one all the way below. What it says to then do is multiply the number below the line by c, and sometimes I'll refer to this as c. C is often the shorthand for the intercept or the root of a polynomial. And in the case of x minus 2, another way that I think is helpful to remember this is what is the 0 value of that factor? If I were to plug in x is equal to 2, that would make that 0, right? Because 2 minus 2 is 0. And that's another way we often reference c as the 0 or the root. So if that makes any sort of sense, that's a way that you can help remember what is c for the reference point. But notice it's phrased as x minus c, x minus 2. That's why we just put 2 only. Change the sign. But anyways, we're going to multiply this. Basically, we're going to multiply the number below the line by c and put that result directly underneath the next inner number. So basically, 2 times 2 is 4. I'm going to put that right here. What it says to do next is add that number to the number above, then put the sum under the line. So like this line right here means add. So we're going to always be adding. It's kind of like I'm going to multiply, add, multiply, add, multiply, add, multiply, add. And that's really all we need to do. So I start by multiplying, I add, negative 3 plus 4 is 1. Then I'm going to multiply 1 by c, the original number here. You don't need to circle your numbers. I'm just doing that to try to emphasize what I'm discussing. Let me actually erase all that just because it's cluttering up the screen. But next I do 2 times 1 is 2. Put that here, which is 2. Always put it above the line. Then I add to the number above to get the number beneath the line. Then I'm going to multiply the new number by 2, which is negative 2. Add them together and get 0. And if you're kind of paying attention to the answer that we got when compared to the answer we did over here, notice that what I get beneath the line is exactly the quotient. And the very, very last number is always representative of the remainder. And this is really important because, first of all, you want to. It's helpful to learn how to do synthetic division because it's a super, super fast way of getting the answer. But also being able to interpret, well, what does the answer mean with respect to the original polynomial? But basically, the last number on the right that you're going to get is always going to be your remainder, and all the other numbers are going to be the polynomial. Now, since they're just straight numbers and not terms, what you have to know about that is that each one of these is arranged by degree. Because like if we're looking at over here, notice the coefficient 2x squared plus x minus 1, same exact coefficients as those three numbers. But a way you can remember it is the one on the second most right is always going to be constant, then it's going to be x squared, and so on. For harder and harder polynomials, you might have more and more numbers to it. It just depends on the scale of those in terms of writing your answer. But basically, the way I write my answer is going to be the same. Well, I could conclude that those two polynomials were divisible, and the answer is 2x squared plus x minus 1 with no remainder. Now, if you do get a number here, there's still going to be a remainder, like I was saying before. But let's do a couple examples, because again, the main benefit of synthetic division is that it's fast. So let's speed it up a little bit and just replicate that process for a few more. So let's say I wanted to take 2x squared minus x minus 3. So I'm going to put just the coefficients in the inside right there. And I want to divide by x minus 3. So I'm always going to take the opposite sign, put it here. Well, to do this, I'm just going to repeat exactly those same steps. I draw a second line below, always drop the first number. Then it's going to be multiply, add, multiply, add, multiply, add. So 3 times 2 is 6, add 5. 3 times 5 is 15. Add 12. I am now done. I just did all the division. And the answer, the last number is always going to be the remainder. And this is always going to be the quotient. And the thing to remember about the quotient is that's technically a polynomial with a sequential order to the degree. So that would be 2x plus 5. Because the second to the rightmost number is always constant. So basically, this is going to be linear because there's only two numbers, and this would be degree 1. And then the remainder would be what's left over. Now, something I forgot to mention in my previous videos is that what's another way of writing the remainder, a more common form of a way of writing the answer to a polynomial. And so circling back to the original example, a lot of times when we're writing the answer to a division problem, we write it as a fraction. Like in the case of when we were doing our long division, we had 4,176 as an answer, and I was like, well, we could write it as R9, but that's kind of how little kids will write it, for lack of a better way of saying it. Not that there's anything wrong with it, but another way to write it is using fractions, and the same thing can be applied for polynomials, which is how I typically. My dog just sighed at me. I guess he wants to go out or something, basically, how would we write it using a fraction? But if I went back to, and I really should have put this in the previous video, sorry for interjecting it here. But basically, the way I could write it as a fraction is, well, I have the whole result, and the remainder is technically not been through the division. So if I want to write this as a fraction, the way we write it is, well, I have the quotient, which is the full part of the answer, and we often use mixed number notation as another way of writing the answer to a division problem, right? Because technically 9 did not pass through the division of 13 because it's on the bottom, it's not on the top. And so basically it's always quotient plus remainder over original divisor as another way of writing that number. Now, like in science and math, we typically don't use mixed number form, but when it comes to polynomials, it's a different way of writing our answer. And so I wanted to just mention, how do we write it? How do we write the division as like a net computational result if I wanted to use fractional form? Because personally, I think that is the smartest way to write our answer, not using the whole DQR thing that I was saying before. But instead, like in this case, we had, well, we were trying to do this divided by this. And let's say I just wanted to write the net answer. Well, that would just be equal to the answer is 6x minus 2. But basically, I had my remainder, which was not passing through division, and it's always divided by the original divisor. And we always want to write a plus here because like it's always the quotient plus the answer divided by the remainder. Sorry, the remainder divided by the divisor. But basically, the setup here is the same. And if you're having trouble remembering, well, where do things go in my fraction, it's always q plus r over d. If I were to write it in this other form, instead of dq plus r, it's just a different way of writing it, because this isn't really the answer. If I'm using this, I'm using it as a way to factor the original thing. If I'm writing it right like this is more standard, because this is like, well, what's the net result of the division? And over here, it's kind of the same thing. It's the quotient and the remainder over the divisor. So if you remember your basic fractions, it's exactly the same for polynomials, and that's my point. But moving back to over here, if we're trying to write, well, what's the answer to our division problem? Like, what's that equal to? It would be equal to the quotient plus the remainder over the original divisor. And basically, this would be my answer. What's the answer to division? It would be, well, what was the whole component, and then what is the fractional left over? But basically, synthetic division is very, very fast and easy way of dividing polynomials, specifically when it is a linear factor. Also, I wanted to interject here. Well, why does it work, and why do I have to change the sign? Because that's something I kind of skipped over before. But if you remember, when I was doing long division, I focused on the steps match, multiply, subtract, and then I repeat. Well, notice that when I'm doing this, what I'm doing is I'm multiplying and adding. So the reason why I want to change it from a -2 to a +2 is so that when I match, I don't have to change the sign. So the reasoning for switching the sign is now I'm allowed to add instead of subtracting. You could have left this as a negative, but you would have then had to subtract instead, and that's just a bigger headache, because then you have to subtract negatives and so on. It's easier to add, which is why we change that sign. And if you're also wondering, how do we get rid of all the x's, where did those all go? Well, basically, we're focusing on what's important. How do we match them up, which is always going to be notice that the number that I dropped through is always going to be the matcher, which was the number I started with here too. Then when I multiply, what I'm going to get is the 2, basically I'm doing 2 times 2, it's whatever was left over, which leaves me with 4. So notice that 4 matches that number right there. Then when I'm adding those together, it's the same thing as there, it's leaving me with 1. Then after there, I'm going to match them. That's always going to multiply into the next number 2. And since I'm multiplying into +2, it's also changing the sign, which creates a 2 here. Basically, it's simplifying that process down to exactly what's going to happen, making it as easy as it possibly can be. That's why synthetic division is awesome and why you need to know it going forward. Let's do one more. This video is getting too long because I'm jumping around a little bit, sorry. But let's just do one more and wrap it up. So with example B from number 3 on the packet, again, we're always going to start by writing the first polynomial inside, only writing the coefficients. Also, this one's an important example because notice that what I said about when we're missing polynomials, or when we're missing terms of particular degree, we have to plug them in as 0. And I said, well, you can do this, and it's helpful when I was talking about doing long division before. But when it comes to synthetic division, you absolutely have to include missing terms, because how synthetic division works, it only works if everything is sequential in degree order, right? Because this was a constant degree 1. If I skip to degree 3, the whole synthetic division process is just not going to work right. So basically, if you have a missing degree term like no x squared, just remember to insert a 0 in the proper place. Very easy to forget that, but do your best to remember that. And we always want to change the sign on the binomial, the constant term of the binomial, out in front. Then, now once I've got the setup done, it's just a matter of quick arithmetic. So drop, multiply, add, multiply, add, multiply, add, multiply, add. And after all is said and done, I'm now done with my division, so I want to interpret the answer. The last number is always the remainder, so we can quickly see, okay, these two polynomials were not divisible. Same with over here, because anytime we get a r is not 0, they're not divisible. And the result of my division, the quotient, is right here. So we would say that the answer to our division problem is 3x cubed. And this one is cubed because it's always, again, it has to be sequential. And another way you can remember it, as I said before, when you're dividing polynomials, they're always decreasing in degree by the degree that you're dividing it by. So if I started at degree 4 and I'm dividing by degree 1, it's always going to lose 1 degree and go down to 3. But basically, it's going to be 3x cubed minus x squared plus 4x minus 4. And it's going to be plus the remainder divided by the original divisor. So my final answer to my division problem would be that. And so again, the importance of this video is synthetic division is quite easy once you know the steps, but we still need to be able to interpret the answer. Ultimately, awesome shortcut. And if you're ever struggling, or if you're not sure if you're doing it right, you can always divide these the old-fashioned way, or using long division to make sure, though that's a lot more tedious. If I had to choose, I would always choose to do synthetic division. But again, I've taught it a lot. For me, I'm very practiced at it. It's something where I could do in like 10 seconds, get that answer, figure it out. And synthetic division was actually a really important tool for mathematicians that they developed in the study of polynomials, because back before calculators, it was much, much harder to do all this. They had to do everything by hand, whereas today we can do polynomial division with certain types of calculators, not most hand calculators though. But anyways, synthetic division was developed, I forget exactly when, but after it was developed, it became so much easier to actually divide the polynomials that they could figure out whether or not polynomials were divisible, again, like in a matter of 5 or 10 seconds. Very important skill for factoring polynomials. And as we move forward in the next couple weeks, we're going to be using synthetic division a lot to factor polynomials and to help us test, well, is this divisible or not? Anyways, that will wrap up for this lecture module.